Before starting, I just want to thank you for having me today. I hope you'll find it interesting. So let me start with the outline. So first, I'll give some motivation about the problem. I will describe the relationship between self-interventions and structural causal models, which is the framework we use to raise the problem. I'll discuss the concept of transportability, just for the sake of understanding the task. I'll describe a symbolic solution to the problem that we formulate, then an algorithmic solution to the same problem, and I'll just give some conclusions. As I mentioned before, this presentation is based on a paper called General Transportability of Soft Interventions, Competence Results, which is joint work with my advisor, Elias Barimon at Columbia. Okay, so establishing the effect of policies and interventions is a task that we find many empirical sciences and other fields too. Even though controlled experimentation is like the gold standard to learn causal effects, it turns out that in many situations, the experiments do not generalize, at least directly, to other domains different than the domain where they were performed. And there are many significant problems in the sciences that can be phrased or that belong to this category when, even if we do experiments, we still need to generalize them. In causal inference literature, and specifically in the non-parametric setting, this problem has been studied under the rubric of transportability theory. Even though there are no sufficient and necessary conditions to solve this problem in the case of atomic interventions like do interventions, these are the first results we have for soft interventions or policies that are not necessarily a do intervention. Specifically in this task, I'll discuss the task of generalizing policies or soft interventions from a collection of heterogeneous data sets that may include observations and experiments. Some possible applications of this theory are predicting the impact of public policies in a country using data from different countries, adapt a classifier to a new domain using the least amount of data you can from that deployment or target domain, recover the results from an experimental study carried out in a population that is not a good representation of the overall population you want to say something about, combine different experiments like I/B testing, multivariate testing to figure out the effect of some new policy that you haven't tested in a certain domain. So now let me describe formally what I mean by soft interventions. But first, a little bit of motivation. So even though sometimes we can identify a do effect from observational data or even from a randomized experiment, it may be the case that there are not enough resources to actually implement this policy in the field. For instance, in a tutoring program, there may not be enough teachers to cover all hours needed to tutor every student, even if we identify the effect of even tutoring to everyone. Also, the effectiveness of the intervention may not be guaranteed. Even if we assign treatment to all patients, they may just not follow it. Just to be more concrete, let me give you an example. Let's say that we have this causal diagram with 4 variables. We observe the GPA of a group of students at the beginning of a term. We observe the motivation level they have, whether they get tutoring or they on their own volition, which depends on their motivation, and we see the GPA at the end of the semester. If we use many different machine learning methods, we may be able to predict very accurately, if we have enough data, what's the probability of someone having a certain GPA given the GPA they had before, their motivation, whether they got tutoring or not. Specifically, this data that we observe represents the current or natural regime students are deciding if they get tutoring or not of their own volition. But now we would like to assess the effect of a new policy for tutoring. So suppose that the resources are limited and we want to give tutoring to students that need it the most. So instead of letting them decide where to get tutoring or not, we'll make it mandatory for students with low GPA at the beginning of the semester. Basically, we are making the distribution of X given W, which was the GPA at the beginning of the semester. We are changing it so that deterministically, they will get tutoring only if they have a low GPA and they don't get tutoring otherwise. So this is the natural regime again. The intervention that we want to make, I'll represent it here with sigma x, saying that I'm changing the mechanism for x, and the mechanism here will become an indicator function of w. So the diagram, I can represent the system after intervention with another causal diagram, which would be this diagram to the right. An interesting thing to notice here is that with the change of mechanism, we also change the parents of x in the graph. Before, x was a function of the motivation of the student. Now it is a function of the previous GPA and not of the motivation anymore. So we can have changes in the causal structure until with some restrictions, like not generating cycles and so on. But that kind of change in structure can occur. Specifically, we use these square nodes annotated with the sigma sub, the set of variables that we are changing, to indicate that there was a change on the mechanism for x compared to the original diagram. So this is more like annotation of the graph in this case. The distribution of the GPA after we make the intervention, we represent as P of y semicolon sigma x, something similar like y given to x. But here, sigma x could be a do intervention or a conditional intervention, as in this case, or maybe stochastic. So for types of interventions, as I mentioned, we could have do interventions that just set the value of the variable to a constant. Like in this context would be every student gets tutoring or nobody gets tutoring. Conditional, when we set the value of x as a deterministic function of some other variables in the graph, like the situation I just described. Students get tutoring only if they have low GPA, and it could be a stochastic where the variable x now follows a distribution conditional on some set of variables w. Like students with low GPA enter a raffle for some amount of the spots, and other interested students can enter a raffle for 20% of the remaining spots. So this is for soft interventions. Now, I'd like to talk a little bit about transportability and what it means. So let me start by saying that different data sets could have different dimensions. Specifically, we could have different experimental conditions. Some could be observational, some could come from a do experiment, from a soft experiment. We could have data from different populations, different cities, different countries, different species, in general, different domains. They could have sampling selection bias. There was something that we studied that also affected the way that we got our samples. And we could be measuring different sets of variables, or we could have missing values. And there are some other dimensions, but these are some of them. Specifically transportability, before that, there are names that this has been given in the literature. For instance, having different experimental conditions can be seen as surrogate experiments, using experiments not on the variable of interest, but others to figure out the effect that we really care about. Transportability comes under the rubric of having different populations, sample selection bias for issues with the sampling mechanism, and partial observability for having just some variables here and some variables there. Specifically here, we'll think about these two first dimensions, having different experimental conditions and different populations as the input for this task. So suppose that we have different domains. We will name them pi star, pi 1, pi 2, etc. And pi star represents the target domain where the effect of the policy is to be identified. For instance, this could be using experiments on mice to assess the effect of a treatment on humans, or use data of a study carried out in Los Angeles to estimate the impact of a new policy in New York City. Usually we will assume that there is a causal diagram augmented with some nodes that will represent differences. I'll get into the details in a sec. But let's say that we have one domain, LA, for instance, and this is domain pi in this equation, and we have observational data, and we have a controlled experiment in Los Angeles too. Here is P of V, where V is the set of observable variables, and sigma x, do x. This is just saying that we run an experiment where we assign treatment and control. and the usual kind of experiment. And then we want to say something about New York City, which is domain pi star in this case. And we do have some observational data in New York City, but we want to avoid repeating the experiment or doing a new experiment in New York. Still, our query here would be the effect of a new policy, which is conditional on this variable z here on y in the context of New York City, this quantity here. Okay, so as I mentioned here, the square node is used, the green square node is used to indicate the differences between the domains. So the assumption here is that there is some variation in the distribution or mechanism for the variable z in the two domains. It could be something like the distribution of age or the distribution of ability to use language properly or writing, anything that could have a variation between the two populations. So formally, we assume that each domain corresponds to or has an underlying structural causal model. I'm not going into the definition of a structural causal model, but I can say that it's a mathematical object that describes the causal mechanisms of some data generating model. And we can usually represent the structure of this model using a causal diagram. And specifically here, we will augment this causal diagram with square nodes, and we'll call it selection diagram. So this is the selection diagram from before. This is a square node pointing to z, encodes the assumption that the function associated with z in one domain is different than the other domain, or that their distribution or the distribution of the latent variables or the noise or the error for this variable z is different between the two domains. The goal of the task is to get an expression that is equal to the quantity of interest in terms of the data that we have. So we say that quantity or this query is transportable if it can be written as a function of the available input. In this particular situation, we can write this query as this expression where we are kind of reweighting two quantities. The first quantity comes from the study in Los Angeles, these randomized trials. So we have P of y given to x comma z. So it's like the conditional or the z specific effect of x and y in Los Angeles. We have another term, which is observational data from New York. You can think of this as recalibrating the conditional or the z specific effect from Los Angeles according to the distribution of z in New York. And then we have this term in the middle that is given by the intervention that we are making, because we said that x will follow a conditional function on z. So the behavior of x will be determined by this function once we know the value of z. So the three terms in this expression are either estimable from data or defined by the intervention. Then we can compute our effect of interest, and we call this the transportability formula or the transport formula. So formally, to summarize the task, we have a target query of interest. We have a selection diagram that represents the causal structure plus the differences, or our assumption about the differences in the domains. We have several data sets, one or more, from different domains, different experimental conditions. And what we would like to say is whether it is possible or not to get a transport formula. So when we say no, this means that for there exist models that induce exactly the same data. Like we could have a set of structural causal models representing this causal structure, exactly this causal structure with these differences, inducing exactly the same data, but giving you different results for the query. So our conclusion in that case is that we cannot say for sure what the target effect is, because there are different explanations for the same data and the same causal structure. So in contrast, when the answer is yes, we obtained a function of the input that is equal to the query of interest for any model that satisfies the assumptions that we have. And that would be the transport formula in the example before. So let me give you another example. Let's say that this is our selection diagram, and we would like to assess the effect of a stochastic policy. I'll call it sigma star, that is made of two changes. So we are going to intervene the variables x1 and x2, and this is the way we are going to do it. So first we have that the change for x1 would be setting it as a marginal distribution specified by the user or the policymaker. For x2, we have a conditional policy. So x2 will follow this conditional distribution given x1 and z. And we would like to know what's the effect of this intervention on y in a particular domain pi star. And we represent this quantity as p star of y semicolon sigma star. For this, for inferring this quantity, we have two sources of data from a domain pi1. You can think of it as a town, country, population. We have a randomized trial where both x1 and x2 were assigned different values at random jointly. So it's a two intervention, a clinical trial on two variables at the same time. We also have data from pi2 where they applied another control study, but there was a conditional policy. So the value of x2 was defined as a function of x1 and z. You can think of it as a medical protocol, for instance. Depending if the patient has these conditions, then we will give this treatment or this other treatment. But it is known exactly what was the policy that they used. We have the selection diagram, which is the one to the right here. Let me note that for each one of these distributions, we could have a graphical representation. So for the query, we have this representation. Here, these bidirected arrows that are now a little bit transparent, it means they have been removed because we have intervened x1 and x2. So x1 is not a function of anything else anymore. In particular, it's not a function of the hidden confounder or this variable that we didn't observe that was affecting both x1 and z. That variable does not affect x1 anymore, and we use the square node here to signal that we changed the mechanism for x1. x2, it's still a function of z and x1, so these two arrows remain, but this bidirected arrow is not there anymore because of the same reason. Now it's deterministic, or even if it is a stochastic, it is not shared, the confounding with y. We could have another diagram for the data available in domain pi1. So the experiment there were two experiments. So in that situation, the x2 was not a function of anything else, just fixed to a value, the same for x1. And we have this green square node that says, or that compared to pi star, there is a difference in the mechanism or distribution for y with respect to between pi star and pi1. And then for the second source of data, we have something similar. Now it was a conditional intervention on x2. So again, we don't have this bidirected anymore. Now the difference is on the mechanism for z when comparing pi2 and pi star. One way to solve this is through a symbolic solution. What I mean by this is using something like dual calculus, but not dual calculus, but sigma calculus. So this is a result from other of our papers. This is a generalization of dual calculus to the context of soft interventions. So you won't see do, but sigma in these expressions. The rules are very similar. We could remove or add things between expressions. So in this case, there is an observation on a variable t, and we are removing it as long as we find some separation in the graph. This is very similar to this separation, just in the context of an interventional graph. We have another rule that allows us to remove or change a regime, removing an intervention, adding an intervention, a soft one, as long as you observe the variable that is being intervened. So we're changing the sigma x for no sigma x while we are observing the variable x. And there is another rule that allows us to do the same, but when we are not observing the variable x. All of these rules respond to a certain separation statement that you can check on a couple of graphs derived from the original one. But I'm not going to parse it right now, and you don't need to parse it right now. I just want to describe that we can use rules and test the separation statements to apply them and find a solution for that. So we can start by writing the query of interest here to the left, and we can sum over the variables, other variables in the graph. And I will use just the chain rule, like probability actions, to open up this expression a little bit. Now I have 4 factors to the right, and I will address each factor individually. So these two factors are given by the intervention because they are the distributions of x1 and x2, and they depend only on the intervention. So I can just plug in the distributions that were given in the intervention specification, these p hats that I defined as the distributions that we wanted to implement. There is this other term on Z. So this term, we will try to find what is this probability using the data that we have available. So we can apply the rules to massage the expression a little bit. So here I'm changing the intervention from an intervention on x1 and x2 to just an intervention on x1. Then I'm changing the intervention that was defined in domain pi star to the intervention in the domain pi 1. And then I'm changing the distribution from one domain to another. And again, each step here I can justify using the sigma calculus and checking the different graphs. What you need to remember here is that this factor associated with the query in the target domain can be shown to be equal to this factor associated with a distribution in one of the source domains. I can do the same for the other factor here. Again, I can use the rules to massage the expression until I get one expression that is in terms of the distribution that I have and that I know it's equal to the distribution that I needed from the target. So I can compose the query here using these four terms, where again, each term either comes from one of the input distributions or is defined by the intervention. So one result that we prove here is that sigma calculus and basic probability axioms are sound and complete for solving this task in a non-parametric setting, given the graph and specification of the input distributions that you have. Another way to solve the problem is through an algorithm. So I'll quickly go over this. In order to do this systematically, we do something similar to what usually we use Bayesian networks for, which is factorizing according to the families in the graph. The issue is that when there are latent variables there, we need to extend this notion of locality that is broken because of the latent variables. We need to extend it. So there is a concept called C factors. A C factor is a product of these kind of families, but they are grouped based on these latent groups that we find in the graph. In particular, we can write this Q function as this product, and this Q function over the set of all observables is just equal to the observable distribution. So using this notion of C components, which are the components in the graph connected by directed arrows. In this case, for these 5 variables, we have 2 components, B1, B3, B5 are in the same component, B2, B4 are in the same component. We can start factorizing a situation like this. So this is the query of interest. We can sum over the variables in the graph as before. Then now we can write it in terms of C factors. And now we can factorize those C factors and figure out each C factor individually. And now we can do this systematically following an algorithm. So again, we have 2 factors that are associated with the intervened variables, and they will be given by the intervention, by the policy that we want to implement. And then we need to find these other 2 factors from the available data. So we can transport a C factor from one domain to another, as long as there are no square nodes pointing to it. So in this example, these C factor associated with Y, we could transport from domain pi 2 because there is no difference between Y in pi star and Y in pi 2 because there is no square node pointing to Y. Similarly, for this factor associated with Z, but now we can transport it from pi 1. So if we follow the algorithm, we could get these factors again as functions or expressions of the input distributions. These are very similar to the ones I derived with the calculus before. And then again, we can express the query, changing again the C factors for the expressions that we have. What we can prove here is that following this procedure, which is in more detail in the paper, this is sufficient and necessary. Meaning, if this algorithm says no, it means that you can prove that there are models that contradict or that work as a counterexample. And if it is successful, then it will output a function like this, and it can do it efficiently in time polynomial to the size of the input. Just to conclude, the problem of assessing the effect of a policy in a target domain using a combination of experiments and observations from multiple domains can be solved in the non-parametric setting with the help of a selection diagram encoding our assumptions about the structural the causal structure, and the differences between domains. We give necessary and sufficient graphical conditions that I didn't talk in detail here, but you can find in the paper if you are interested. And this graphical condition, you can check the graph and say, with respect to the query, if it is identifiable or not. Then we have a complete algorithm that I briefly described the strategy that again determines the transportability of a query given these inputs. And we prove that the sigma calculus is complete for this task, so you can employ it for that. Thank you for listening, and I'm open for questions.
Thank you, Juan. If you have any questions for Juan, please feel free to write them in the Q&A. At this moment, we don't have any questions. So as questions come in, you can either answer them in the chat, or if you point them out to me, you can answer them live at the end of Nicolas' talk.